Hi to all. In this video, we are going to see about specific magnetic loading and specific electric loading. Okay, and what are the factors we should take when we go for magnetic loading and electric loading? Okay, uh, so specific magnetic loading. The term P pi represents the total flux. Okay, and it is called total magnetic loading. P pi is nothing but total magnetic loading. Magnetic loading per unit area of the armature surface is called specific magnetic loading. Okay, the unit area magnetic loading per unit area of the armature surface is called specific loading or average flux of the flux density in the air gap, BAV. Okay, BAV is equal to BAV is the specific magnetic loading P pi by pi dl Webers per meter square or Tesla divided by so before from this equation we can rewrite P pi is equal to BAV by pi dl. Okay, following are the factors which influence the performance of the machine for magnetic loading. Okay, the iron loss. A high value of flux density in the air gap leads to higher value of flux in the iron parts of the machines, which results is increased iron losses and reduced efficiency. So we should, if you go for high value of flux density, what will happen? The losses which will be in the iron loss will be more, because high flux density, the higher value of flux density in the air gap leads to higher value of flux in the iron parts. Because of that, iron losses, okay, and because of this, the efficiency also will reduce. Voltage, second one, when the machine is designed for higher voltage, space occupied by the insulation becomes more, thus making the teeth smaller and hence higher flux density in teeth or core. If you go for high voltage, then the insulation needed will be more, because it should withstand the particular voltages. In that case, what will happen? The size of the flux, that smaller, okay, the teeth size of the iron part will be smaller, hence the higher flux density in teeth and core. Transient short circuit current. A high value of air gap density, a value of gap density results in decrease in leakage reactance. Okay, if the high value gap is there, so leakage reactance may occurs more. Okay, hence increased value of armature current under short circuit condition. Okay, the value of gap density will be more, then the leakage reactance also more. Because of that, armature current under short circuit conditions may increase. Stability, the maximum power output of a machine under steady state condition is indirectly proportional to synchronous reactance. Okay, the power output indirectly proportional to synchronous reactance. If higher value of flux density is used, it leads smaller number of turns per phase in armature winding. This results reduce the value of leakage reactance. Okay, the leakage reactance value will be reduced, and hence increased value of power, and hence increased steady state stability. Okay, if you go for high value of P pi BAV, then stability also increases. Parallel operation. Okay, next one, the satisfactory parallel operations of synchronous generators depends on the synchronizing power. Higher the synchronizing power, higher will be the ability of the machines to operate in synchronism. The synchronizing power is inversely proportional to the synchronous reactance, and hence the machines designed with higher value of flux density will have better ability to operate in parallel with other machines. So if you go for higher value of magnetic flux density, then some of the advantages are also there, some of the disadvantages are there. One is parallel operation, it is easier, and stability will be good, and transient is a drawback. Okay, under short circuit conditions, increase the value of armature current under short circuit conditions. Leakage reactance will be leakage will be occurs, that is drawback. And voltage, the value of the heat will be generated more, and occupied installations becomes making teeth smaller. So this will make flux density in the teeth are more. Okay, iron losses will be more. So if you choose the specific magnetic loading, it should not be um, more iron loss percent, like that. We should choose the magnetic loading, specific magnetic loading. Okay, values. Next one, specific electric loading. The term IAZ by A represents the total armature conductor or total electric loading. This one, IAZ by A, is nothing but total um, electric loading, and is called electric loading. Electric loading unit length of our periphery is called the specific electric loading. Q is equal to pi d by P. Following are the some of the factors that influence the choice of specific electric loading. Okay, copper loss. If higher the value of Q, larger will be the number of armature conductors, which results in higher copper loss. Okay, in a particular place, we are placing a more number of coppers, then the heat will be generated. Because of that, losses will be present there. That losses, copper loss, will be high if you go for higher value of Q value. Okay, voltage, a higher value of Q can be used for lower voltage machines, since the space required for the insulation will be smaller. Suppose voltage, in the case of higher value of Q, for a low voltage machines, spaces will be more. Okay, so there we can go for higher value of Q. Synchronization reactance. Okay, next one is the synchronous reactance. Higher value of Q leads to higher value of leakage reactance and armature reactions, and hence higher value of synchronization reactance. Such machines will have poor voltage regulations. Okay, lower value of current under short circuit conditions, and low value of steady state stability limits, and small value of synchronizing power. So synchronous reactance value will be increased. This will be the one of the drawback for the higher value of Q. Okay, copper loss also will increase when you go for higher value of Q. Stray load losses. With increase of Q, stray load losses will increase. Value of specific magnetic and specific electric loading can be selected from design data handbook for salient and non-salient whole machine. If you go for a higher value of Q value, these are the things. One is stray loss will be high, and synchronous reactance value also will be high, and uh, voltage value also high, and copper loss value also high. To overcome that, we should not go for a very high value of Q, as well as we should not go for a very low value of Q. If you go for very low value of Q, what will happen? The efficiency of the machines will reduce. Okay, so these are the factors we should consider when you go for Q value and VAV values. Okay, thank you.